Hey there, chemists. We are going to start talking about gases in this lesson. Today, we're just going to look at how pressure is measured and different units of pressure, and then how some of the properties of a sample of gas relate to one another, and close with some calculations using what's called the ideal gas law. So, first of all, on your notes are some pictures of some old devices that are used to measure pressure of gases indirectly by looking at what it does to a fluid. A barometer, shown on the left there, measures atmospheric pressure, which effectively just says how much is the atmosphere being held down by gravity compared to a vacuum. And we measure the height of a liquid level, historically mercury, to see what the pressure of that gas is doing. Right next to it, what's called a manometer is essentially the same principle, but you're measuring some contained sample of gas against an atmosphere, and it just measures pressure differences. So the difference in liquid height, really in both cases, tells you the pressure difference. A barometer just measures it against a vacuum. So let's look at the manometer more closely. Let's say we have some atmospheric pressure of 760 millimeters of mercury. That's roughly what sea level atmospheric pressure is. And I have some gas contained in that flask there. I want to know what is the pressure of that gas. We can measure the height difference between the two liquid levels. Let's say we do that and we get 32 millimeters of mercury. Not a whole lot of a difference, but it's that's different between the atmosphere and the gas. Well, make a note. It's important to realize how to read this device. A lower liquid level, whoever's got the lower liquid level, in this case the atmosphere, has a higher pressure. That's because the gas is actually pushing down on that side more than the other side. They're both being held to the surface of the earth by gravity, but whoever has the higher pressure will push down on that fluid level more. So the atmospheric pressure is higher than the gas pressure. By how much? This much, 32 millimeters higher. So if I want the pressure of the gas, I simply take the atmosphere, and in this case, I subtract the height of the liquid level difference. So 760 minus 32 gives us 728 millimeters of mercury. And you might be wondering, what do we do with a millimeter of mercury? That's a length and an element. Yeah, that is a pressure, because we're indirectly measuring the pressure of a gas based on what it does to a height of a fluid, in this case, liquid mercury. That means I need to be able to convert from one pressure unit to another. Millimeters of mercury are by far probably the most common one that you'll see in AP chemistry this year. And it's important to note that one atmosphere is 760 millimeters of mercury. That is the most common conversion you will have anytime you're dealing with gases in this course. It happens to equal the same number of torr, named after Evangelista Torricelli. They're both 760. And you might see some other units as well. The SI unit is the Pascal. There are 101.3 kilopascals in an atmosphere. And then less commonly seen here, but you might see it elsewhere, is pounds per square inch. That's 14.7 psi. So all of those equal 1 atmosphere of pressure. And we just have to know how to convert from one to the other. In fact, let's do that right now. Let's say I have 190 millimeters of mercury. What is this in ATMs, in atmospheres? So how many atmospheres given 190 millimeters of mercury? Use dimensional analysis. There's one ATM per 760. So I take 190, I divide by 760, you should get a fourth, 0.25 atmospheres. So those are some units of pressure, how we convert between them, and then how we measure them with these devices based on fluid differences. Now let's look at some properties of gases, such as not just pressure, but their volume, their temperature, and their amount, and how are these related? You should have learned these gas laws back in your introductory chemistry class, and I'm just going to review all 4 of them right now. And before we do that, let me just show a quick animation of a sample of gas. Here's a simulator that has particles of gas represented by spheres. They're bouncing against the walls of the container. That's what's causing some given pressure. I just want to observe what happens as we change some of the conditions of this gas. Right now, it's in some fixed volume, represented by the area of the screen. It's at some temperature, and there's some amount of it in there, some moles of gas. Notice what happens if we decrease the volume as a result of giving it a smaller space. I just zoomed in and gave it less volume. The pressure increased by quite a bit. So as volume gets smaller, pressure gets bigger, and vice versa. If I increase the volume, it spreads out. As volume increases, pressure decreases. It's called an inverse relationship. We can show a few other relationships on this simulator. I can add more particles of gas if I simply add more spheres of atoms in this case. If I increase the number of atoms, the moles of atoms, but the temperature and the volume are the same, the pressure goes up correspondingly. If I were to decrease them, it would go back down. We can even show temperature in this simulator. I can cool this sample of gas down, and you'll notice the temperature correspondingly causes the pressure to decrease. You'll also notice the speed of the particles changes. We'll talk about that in a future lesson. So let's write down some of these relationships. The first one we saw was the inverse relationship between pressure and volume. As one goes up, the other one goes down, which means if I plotted pressure and volume, I would see an inverse relationship that looks like that. All the others are actually direct relationships. Charles' law relates volume and temperature. If you plot the volume of a gas versus its temperature, you get a very linear, direct relationship. Likewise, with Avogadro's law, we saw that in the simulation just now. If you plot the volume of a gas versus the amount of it in moles, you get a linear, direct relationship. And then Louis Gay-Lussac's law relates pressure and temperature. If you plot the pressure of a gas versus the temperature, you also get a linear, direct relationship. This is one way you can actually experimentally determine what absolute zero is. If we extrapolate the pressure-temperature graph down to a zero pressure, that actually would become a zero temperature, 0 Kelvin. And that's where absolute zero comes from. If you have zero pressure, you have zero temperature, theoretically. We can combine these into what's called the combined gas law. That's the product of pressure times volume divided by temperature at some initial condition, P1 V1 over T1, is equal to the product of the pressure and the volume divided by the temperature at some final state, T2, V2, and P2. Make a note that we have to use the absolute temperature scale anytime we're talking about gases and temperature. It has to be in the absolute scale. So we use Kelvin. Remember that Kelvin is simply Celsius plus 273. Make a note of that if you've forgotten that conversion. There is another scale based on Fahrenheit. It's called the Rankine scale, but we're not going to use that in this course. But it exists if you see it later on. I could actually add one more thing to this combined gas law. What about moles? Well, if you throw moles into this equation, it also works. And not only is it a constant, it's constant for every gas. So we give it its own value and we call it R. And then we get the ideal gas law. Pressure times volume is equal to moles times R, a gas constant, times the temperature. And R is the universal gas constant, 0.08206 liters times atmosphere times divided by mole and divided by Kelvin, which is great because it shows me all the units I have to make sure I use whenever I'm using the ideal gas law. If you're using the ideal gas law and this numerical value of R, your volume has to be in liters, your pressure has to be in atmospheres, and your temperature has to be in Kelvin. So you should know how to convert other units of volume into liters, other units of pressure into atmospheres, and other units of temperature into Kelvin if we're ever using this equation, and we'll do that several times in this unit. We'll also follow up with when this equation really works. I'm just going to tell you right now, it's best when gases look like gases, when they are hot at high temperatures and when they're very spread out at low pressures. We'll talk later about deviations in this, but for now I'll just tell you this law works very well as long as gases behave like gases. If you cool them down or compress them, you start to get what looks like a liquid, and then the ideal gas law does not work as well. But as long as it's hot and spread out, you have a good relationship that you can use here. Okay, let's wrap this up and do some example problems that relate to some of these equations and plug in some numbers. First off, we need to know what standard temperature and pressure stands for. STP is standard temperature and pressure. That's defined as 0 Celsius or 273 Kelvin and 1 atm. And the first question here wants the volume of a mole of gas at STP. So I'm going to take my ideal gas law, PV equals nRT, and I'm going to rearrange and solve for V. If you do that, you should get V is equal to nRT divided by P. And I'm simply going to plug in my numbers. I have 1 mole of gas, so 1. R is that new constant, 0.08206. Temperature is standard temperature, 273. And P is standard pressure, which we just saw is 1 atm. I'll actually say 1.00, just to throw some extra sig figs in there. If you dig out a calculator and plug that in, you get 22.4 liters. And that's a number that maybe you saw in your introductory chemistry class. This is called the molar volume. And it's how many liters a single mole of any gas will occupy at standard temperature and pressure. So it doesn't even matter what the identity of the gas is. All that matters is how many moles we have of it, what pressure it is, and what temperature it is. That lets us get to the volume. Speaking of the identity, that's the very next question. How could we get the identity of a gas? This is multiple choice. Which of these 5 gases would occupy a volume of 2 liters at this standard temperature and pressure and have a mass of 4 grams? Anytime you have to identify a chemical substance, you're probably being asked to figure out the molar mass of that gas. So how does molar mass relate to gases? Let's go over to a blank page for a second and talk about that. If I rewrite the ideal gas law, PV equals nRT, I'm going to substitute N for what we've used in the past. Remember, moles is simply the mass of something divided by its molar mass. So P times V is mass over molar mass times R times T. And there I've extracted the molar mass out of my ideal gas law equation. If I rearrange that, my molar mass is now equal to the mass of the gas times the R constant times T divided by the volume and the pressure, which means it's also based on density. So you could also write this equation as density times R times T all over the pressure. That's the same as the ideal gas law, but it uses the molar mass and relates it to the density of a gas. So if we go back to this question, which one occupies this volume at STP with this mass? We're actually being asked to solve for the molar mass. So the molar mass we just saw is the mass of the gas times the gas constant times the temperature all over the volume times the pressure. The mass is 4 grams. The R value is 0.08206. Temperature is standard temperature, 273. The volume, it says, is 2, and standard pressure is 1 atm. Now, before you go dig out your calculators, take a look at the similarity with this question and the one right next to it. We already figured out what 0.08206 times 273 is. We know what that is. It's the molar volume. It's 22.4. So I can actually rewrite this as 4 over 2 times 22.4, which is just 2 times 22.4. So I get 44.8 grams per mole. And that's how you would do this without a calculator on the multiple choice section of the AP. Looking at the choices, that means I need to go and get a molar mass for each of these gases. Sulfur dioxide, that's 32 plus 2 times 16, so it's about 64 grams per mole. Nitrogen is 2 times 14, so 28 grams per mole. CO2 is 44 grams per mole. C4H8, well, 4 times 12 is going to be 48 plus 8 more, sounds like 56 grams per mole, still nowhere 44. And ammonia is about 17 grams per mole. So CO2 looks to be our closest. It's not exactly 44.8, but it's certainly the closest answer to that. Okay, so there's one more problem. I'd like you to hit pause and see if you can figure out the last question. They say we have a sample of hydrogen, remember that's diatomic. It occupies 10 liters at 0 Celsius and 6.72 atm. We want to know how many hydrogen atoms are present. See if you can figure out how to use the ideal gas law and the information given to come up with atoms. Okay, let's check and see how you did. So they give me a volume, they give me a temperature, and they give me a pressure. That means I can solve for moles of hydrogen. So if I rearrange the ideal gas law and solve for N, that's PV over RT. The pressure is 6.72, it's already in atmospheres. The volume is 10, it's already in liters. R, 0.08, 206. T is 0 degrees Celsius, that's 273 Kelvin. And that's my moles. I'm not at atoms yet, but we'll start with this. Oh, and look, again, we have the product of 0.08, 206 times 273, which we know is the molar volume, 22.4. So my numerator is just the product of 6.72 times 10, that's 67.2, divided by the molar volume, 22.4, and that's a whole number right there. I end up getting 3 moles of H2. But I want atoms. So how do I get hydrogen atoms? We need to do a couple more conversions with this. First, we're going to turn moles into molecules. There's Avogadro's number of molecules per mole. And then if I want atoms, I have to know that there are 2 atoms per molecule because it's diatomic. So I get 3 times 2 times 6, that's 8, that's 6 times 6 is 36 times 10 to the 23 atoms, so that's 36 times 10 to the 23. That means I get 3.6 times 10 to the 24 H atoms when all is said and done. Okay, so that's how we use the ideal gas law to look at different properties of a gas, namely things like its volume, the amount of moles of that gas. All the properties of a gas are related to each other by any of these laws. They're actually all buried in the ideal gas law, and we can convert between different pressure units using any of these conversions and measure it with a barometer or a manometer. Thanks for watching.